Okay, I think we're going to get started here. Um, so today we're doing Unit 11, and that's moving us really back into computational theory, kind of the theory of programming and programming languages here. Um, if you remember, we started looking at some theoretical stuff, context-free grammars, push-down automata, finite automata sort of stuff. Um, and that kind of led us into the underlying kind of structure of our programming languages. And then we delved into kind of the different components, how do we do control flow? How do we do arrays? What are pointers? What are subroutines or functions? How are those handled? And so the middle part of the class was very much focused on programming languages here. And now we're returning to computational theory. We talked about functional programming and logical programming languages last week, but now we're really turning into theory. And the main theoretical component we're going to do is Turing machines. That forms kind of the foundation of most computational theory exercises at work. We have a little radiator making some noise in the background, so we'll see how that goes. So if you're wondering who's playing the drums in the background, that's the radiator. So we're going to look at Turing machines today, try to get a basic understanding of them. And then on Thursday, we'll have you start trying to program Turing machines. Again, this will be a little different. In the past few weeks, we've been kind of working on this. On Thursdays, we'll look at like 3 different languages and do problems with 3 different languages. Now, in this one, we're really only going to do these theoretical kind of programs, I guess, or algorithms, and we'll just be using Turing machines. So under resources, let's just talk a little bit about how different different textbooks cover this stuff. So in other textbooks, so generally in a lot of universities, they'll have a computational theory course and a programming language course, and we're combining those here. And so we're going to look a little bit at theory textbooks and what some of these computational theory textbooks will be here. So here's a well-known one by Hopcroft and Ullman and Moana here, automata theory, languages, and computation here. And again, if we go down to the table of contents, again, they start with automata, finite automata. Let me bring this a little bigger. Regular expressions, regular languages, which are made from regular, then they do context-free grammars and languages and pushed-down automata. And that's kind of what we covered at the beginning of the class. That leads them to context-free languages here. And then they cover Turing machines and go over, the quest to decide all mathematical questions and some of the background of Turing machines, how to program a Turing machine, some extensions to Turing machine. And then they move on. With Turing machines, we can look at undecidability and what problems can be decided and not. And so that's what we'll be getting in now. And then from there, they'll look at what are called intractable problems that are complex, are doable but complex and can't be done in a good amount of time. And that leads us to space complexity, which we'll be doing in a future chapter here. So again, that's kind of a standard route to computational theory here. Zipser is another well-known textbook in this area. Again, this was a little more quickly again, talks about automata, mathematical proofs, regular languages, context-free languages. And then in chapter 3 already jumps into Turing machines, formal definitions, variants of Turing machines, and then decidability and reducibility are topics related to Turing machines. Once you know what a Turing machine is, you can talk about decidability and reducibility here for that. And then gets into time complexity and space complexity, which we'll be covering later on. So we're going to jump in. I'm going to go into this learning resources here and just look at the chapter 11 prompts. I've done these like I did before in Gemini. And again, for your QQSP, you can just grab these blank ones if you want and look at those also for that. So the first prompt talks about kind of relating this to the early chapters: context-free grammars, regular expressions, deterministic finite automata, push-down automata, Bacchus-Nauer format, ways we could define a computer language there, and kind of relate these again and remind ourselves how these are related to each other. A lot of these kind of can determine the same languages here. So regular expressions and deterministic finite automata are equivalent, and context-free grammars and push-down automata are equivalent also. And we looked at Bacchus-Nauer format for describing a language, and that's the same, what you can define with BNF syntax is the same thing as a context-free grammar, which is the same thing as a push-down automata here. So basically, we have these context-free languages. Well, we have regular languages here, which we could set up with a deterministic finite automata. But there are some languages that are more complex here, so we need some memory, and we need context-free grammars or push-down automata to do this sort of stuff. Anything that has some sort of recursive kind of structure in the language, and just simple things like, can you figure out balanced parentheses that are required that you have the same number of left parentheses and right parentheses. That kind of, you don't know how many parentheses the user can put in, as many as they want, and you want to be able to calculate those and match those up. You need some sort of stack or memory to do that. And so we need these context-free languages to do that here. Now we're going to get into Turing recognizable language here, which is our most powerful stuff. And this will be everything context-free languages can do, plus some more stuff here. So again, the next question is, why do we even need Turing machines? And this sort of stuff. So let's look at that. We're going to see is Turing machines will give us a good general computational platform. We'll kind of try to show us anything a real world computer can do, a Turing machine should be able to do. We'll model algorithms. So we'll kind of look at formal algorithms and allow us to reason about the capabilities and limitations of these. The idea is that any program that you write in Java, you can convert into a Turing machine algorithm and prove that it'll run on a Turing machine. And any Turing machine problem you can convert to like a Java program and run it that way. And we'll show, we'll see an equivalence between what we can do with our programming languages and what a Turing machine can do also. And then we can, once we have that theoretical foundation, we can say, well, if a Turing machine can't solve these some problems with an algorithm, then we can't do it in any computer language. So regardless of the different languages that are out there, we won't be able to do it with that. So that's what we're really trying to get at, is understanding computation, set some theoretical foundations for this, and kind of explore this sort of stuff. Like this is saying that these languages can simulate the capabilities of a Turing machine. Turing completeness, a programming language is said to be Turing complete if it can simulate a Turing machine. Most modern programming machines, programming languages are Turing complete. So. One thing we will see is some limitations. Turing machines tend to assume infinite amounts of storage, infinite number of symbols and stuff like that. And so sometimes we'll see that although we can simulate that on a machine, that when we get into some of the infinite amounts of stuff, we will run into some, we'll prove some things with that. But in reality, it really doesn't show up on these things. So let's try to understand Turing machines here. I'm gonna bring up Chat GPT and look at that. So we're trying to just get an understanding. So have you guys seen Turing machines somewhere else? Where have you seen them before? Where? In data structures? Yeah, I could see that. Maybe there. So, okay. So we'll try to look first at an intuitive explanation, and then we'll get into our formal explanation of these stuff for this. So again, the general idea of a Turing machine is that it has a tape memory that you can run, right? Generally, it's a two-dimensional, just a linear tape, and it can move to the left or the right on the tape. Here, let me bring up. That's one of the problems with these AIs is they aren't great with pictures. This is kind of the idea of a Turing machine here is it has this big infinite tape that it can write symbols to, it can wind it to the left and the right, and then it can write things on the symbols here. So that's kind of the idea we're trying to get at, is we have this infinite tape here. We have a head, a reader, a writer. So again, we have some RAID head here that can read the current symbol here or write it. So we basically read or write one character at a time for it. We can erase a character and write a new character in its place, and we can do that as many times as you want here. Idea. The machine has some kind of logic to it, and so generally it has what we call a state machine in it. It has different states. And in each state, it applies different rules. So the rule will look at what's under the tape and then make some decisions on what it can do based on what's under the tape here. So again, we have a finite number of states that represent this. And often we'll draw these out. On Thursday, we'll start drawing these out as state transition diagrams here. And again, this is one thing that I think AI is not very great at, is this sort of state transition diagrams. So we'll talk about like this sort of a diagram where if you are in state A and you see this under in front of you, you can go to state B. From state B, if you see this, you'll do this and stuff like that. So a lot of the programs can be represented as this state transition area, although we'll also just write them out as text. So that's our transition functions, the rules. Transition functions are sort of rules that tell a machine what to do. So like an example, if you are in state A and you see a 1 on the tape, then write a 0 and move to the right and change to state B here. So again, this kind of tries to illustrate all the things. You can read what's on the tape. You can write what's on the tape. You can move left or right, and then you can change the state as an idea. So here's ChatGPT talking about the same thing, the tape, the head, the states, the transition functions here. So again, what to write on the tape, what state to move to, and what direction to move the head. So again, we can read what's on the tape, and then we can write to it, change the state, and move to the left or the right for this stuff. We have a start state. We start up machines here, and you can read through this. So I don't know, you guys like history of computer stuff? Do you know much about Alan Turing and that sort of stuff? Not much. So Alan Turing, is a very interesting historical figure here for this. Let's just talk about it right here. This talks a little bit about this problem. So Hilbert was a mathematician slash, I guess, philosopher around the turn of the century, and to find a bunch of problems that were, challenging problems for that time and still exist largely. And so one of them is basically asking, is there an algorithm that can determine if any given statement in first order logic is true or false? So anything you can write in first order logic, can you, if you write out first order logic, can you then write a program that can always figure that out here? So is there a universal method to created to solve these sorts of problems here? And so this was in 1928. And so Turing in 1936 published a paper on this. And in order to do this, he had to formalize what it meant to be what is an algorithm there and what can it do. So, is there an effective procedure to solve this or to do this? And again, we didn't have a formal definition for algorithm. We didn't have a formal definition of what a computer is. So he defined this Turing machine. Again, this is 1930s. This is before we really had we had some beginnings of kind of mechanical computers, but we certainly didn't have today's computing. But he created a formal kind of logical version, this Turing machine, in this paper to try to prove this stuff. And again, this kind of led to this formalized definition of Turing machines. So this is one of the things Turing did there. So this was 1936, getting near World War II. So then during World War II, Turing was part of a team that was breaking the German Enigma code. And so that's a well-known story. I don't remember what the movie is called. There's a well-known movie about Turing and their work at Bletchley Park breaking the Enigma code. There's another well-known movie just about Turing and his life there. He, again, this was the 1930s. Uh, he was in many ways, again, he did amazing work, really huge work for the war effort, for saving not only Germany in a lot of ways, but much of the world from Nazi uh, war machine. But he was also persecuted because he was a homosexual back then. It was had severe consequences there, and uh, yeah, his story is very tragic. The end of his life came not long after World War II ended there. So, um, yeah, so if you want to dive into the history of a amazing computer person, Turing is an interesting figure to look. And again, there's some movies you can look at if that's the way. There's great books written about him, or you can just do some research on your own on this. So, okay, so let's do a formal definition of a Turing machine here. Uh, so we're going to define in math a machine, a Turing machine M is just going to be made up of these parts here. And so these are our parts. We're going to go through these stuff. So each part, so we need a set of states. So Q will be our set of states. It's a finite, non-empty set of states. And again, we often just represent these by capital letters or by this Q0, Q1, Q2 here. There's also two special states, a Q accept and a Q reject state often in this. So we have this list of states for this. We have our input alphabet. The input alphabet is a finite alphabet for this. Just a set of symbols that we're going to write on the tape. We often have some sort of blank symbol, a space or something like that, and assume that the tape is mainly filled with these blanks here. A common like alphabet would just be to write zeros and ones here. And again, this kind of assumes there's the blank symbol here. So and again, that's just kind of assuming that that is available in all alphabets. So we don't really list the blank symbol in our alphabet here. So that's our input alphabet. And then our tape alphabet is what we write on our tape here. So we'll have two different things. And again, they can overlap. We can write the input alphabet right on the tape, or we can write additional information, onto this tape. So again, this is a finite tape of symbols. So again, this is sigma. So sigma is generally our input alphabet. I think that's gamma. I don't know. I'm trying to remember my Greek letters. I think that's gamma is our tape alphabet here. So again, I was confused. I was thinking about the tape alphabet here. The input alphabet doesn't have a blank in it because our tape alphabet does here. So the input alphabet, we basically it can include all of the input alphabet and the blank symbol there, and we can have additional symbols for computational use to just store temporary information. So for example, if this is our input, if we're just giving it zeros and ones, our tape alphabet might be zeros and ones, a blank or our space, and then some additional symbols like X and Y just to store where we're at. Okay, so we have our states, we have our input alphabet, we have our tape. Those are these first couple, and this delta is the next thing. So that's our transition function here. So we'll write different functions here. So it's a function over our states. Given a state, something in our state and some input alphabet, we're going to produce a new state, something from our input alphabet, and then whether or not we're going to move to the left or the right for this. So our next state, we're going to calculate the symbol to write on the tape here. So that's our tape alphabet, and the direction to move the head. So again, we're given our state and what we currently read from the tape, and we're going to output our new state. It can be the same state, some new thing to write on the tape, and then again, whether or not we're going to move to the left or the right. So that's all we can do with this stuff. So here's an example of a transition diagram. If we're in state 0 and we read a 1 on the state, then we're going to go to state 1. We're going to write an X to the tape and we're going to move to the right. So again, if we're in state 0 and we read a 1, go to state Q1 and write X on the tape. So we'll write X over the 1, and then we'll move to the right here. We have a start state, often labeled Q0, and then we have two special states, an accept and a reject state here. Often we'll be writing machines that'll try to recognize if something is true. So we'll write a Turing machine that will, determine if a set of a sequence of inputs is a palindrome or not, or if we have an odd number or an even number, and we'll have a Turing machine that will either accept that saying it is an odd number or reject it, that's not an odd number for that. So here's our sample for this. We're just going to check if our string consists entirely of ones. So we have our states here, Q0 and Q1, and accept and a reject state. Our input alphabet is just 1. The tape alphabet is 1 and a space. And then we have rules. So if we're in state 1 and we state 0 and we see a 1, we stay in state 0. We write a 1 and we move to the right. So we're just reading all the ones here. If we are in state 0 and we see a space, we go to accept. So that means we've got it to the end of the input for this. So we keep reading 1, 1, 1, 1, 1, and we got the end of the inputs and we did this. So we write a 0 and we shift to the right, and we're now in the accept state. If we see a 0 here and we go to the reject state. You will see sometimes that AI will make mistakes with some of this logic for Turing machines. So if you look at this Turing machine here, there are some mistakes, and we can actually ask. Let's see if we ask ChatGPT, what is wrong with this Turing machine? Oh, I'm on Mini. I should have asked that. The newer models that do some better reasoning are better at finding mistakes in this sort of stuff. We'll see that. So again, what do we run into? The actual problem here is that our alphabet has to have both 0 and 1 in it, and so does our thing. So although we're just detecting if there's ones, the alphabet has to have 0 or 1 in it. So our alphabet should have 0 and 1s so that we can see if we read a 1 or a 0, what's in that. Example of this on the board. Again, the idea here is we have a Turing machine and we're reading something, and we have this long tape for that. And in our Turing machine, we have what state we're in for that. Oh, I think they're using a little q for the state. The idea is that we will accept or reject this, and then what we have to do is load some initial input onto the Turing machine. So maybe we'll have this input here that we'll load in for this. And then we'll go through the states. So we have this different states, and we'll check which state applies. So we're in Q0. And we have, if we're in Q0, if we read a 1 or a space or a 0. So we're going to read a 1 here. And then we're going to modify this. So we're reading a 1. So, and we're in Q0. We're then going to go to Q0, stay in the same state, and we're going to move to the right here. So now we'll be reading here. And then again, which of these states do we have? Again, we're still in state Q0, and we're reading a 1. So we'll do the same thing. So we stay in Q0, still in Q0 here. We're reading a 1, we're writing a 1, leaving that there, and then we're moving to the right again. We'll move to the right again. We're still in that state. We'll read this 1. Stay in Q0 and move to the right. And now we get to do something different. Now we're reading a 0 here. And so we'll switch our state to Q reject there. And we'll write a 0 and we'll move to the right again. But now we're in this reject state. Once we get into the accept or reject state, we basically stop there and don't do anything more for that. So do you get an understanding of what these Turing machines do? They're not overly complicated, hopefully. So let's talk about how we kind of generally configure these. We load in a string of symbols onto the tape here. We then have a state transition, or the current state of the Turing machine here. And so often we'll write out the state of a current Turing machine as this way. We'll write what, like here, if this were our state, we'll write in the symbols to the left of the read head. We'll write the state we're in, and then symbols to the right there. So you can actually do a lot of this computation or tracking with just this sort of stuff. So this just shows that we have a 1 and a 0 to the left. We're in state Q1 here, and then we have a 1 and a 1 to the right here, and then we have a 0 here. Well, actually, I think Q is just their state here. So this is that. So they're just storing each state as a single symbol for this. And again, we can talk about if we apply a state transition, we can change this string, our current state of our machine, into a different state. So like here, if we apply this rule, if we're in state Q and we're reading a 1, so again, we're in state Q and the 1 we're reading is just to the right here. So that's what we do. Now we're going to go to Q state P. We're going to write an X here and move to the right. So again, that'll shift us to the right. So and write an X here. So this will be our result. It should actually be that, I think, where we've we got our 1 and a 0, and we have an X, and then we're now in state P, and then we've have just the 1 left. So we basically have consumed this 1, converted it to an X, and moved to the right. Let's talk about halting, accepting, rejecting. So again, every Turing machine is going to have 2 special states, an accept state and a reject state. There, once we get to those states, we stop there. So again, you can kind of I relate this to like whenever you're running a program, the program runs, and at some point it just stops there or quits. Especially, I'm thinking of more like console input, not an event-driven program, but something where you have console input, you're typing things in, whatever. At some point, you get back, the program finishes. So again, halting is when we get to one of these states. So we don't know if we'll always get to one of those states. So again, if we look at a picture of this sort of stuff, there might be a halting state here. But we don't know if we'll ever actually get there. We might just get into some infinite loop somewhere else where we'll just get and loop or not do anything for that. Or just run out of input and get to some point for that. So again, halting is when the machine halts. We're either in the accept or reject states there. And looping is that when we keep applying the transition functions, and again, we're not changing states, or we're changing states, but we're never getting to that. So again, the halting problem might be that you're in one state, like the state B, and you're just looping in state B, you never move state B. You could also be going from state A to B to A to B to A to B. So you might be changing states, but you're still in a loop here. But you're never getting to one of the final states here. So, and again, we're often asking if the machine accepts or processes some input or doesn't there. So, we just talked about having a Turing machine that accepts a string of 1s. If we give it 1, 1, 1, it will accept it. If we give it 1, 0, 1, it will reject it. One of the things you find with these Turing machines is we tend to do a lot of toy problems to start with. Well, even all the time, we rarely get away from toy problems. So things like palindromes or stuff like that. Is this number a palindrome or not there? And again, we'll either accept it that it is a set of inputs is a palindrome, or we'll reject it saying it's not a palindrome here. I'm not going to go through this next one. It just walks you through more of this information about these transitions and stuff like that for this. Gives you another example. Again, this version is really stuck on this, accepting it something it's all 1s for that. And we'll look at some other examples in a little bit. So next, we're going to talk about what classes of languages can we recognize with the Turing machine. So that's kind of idea is that what can we write? What kind of Turing machines can we set up so that it will recognize certain languages or structures or stuff like that here. So again, we'll talk about a language being Turing recognizable if there exists a Turing machine such that any element inside any word or a string of characters in that language, M will accept it, and anything that's not in that language, M will either reject it or loop indefinitely. And this will be important, reject or loop indefinitely for that. So it never gets to the accept state for this. So for example, you could write a Turing machine for Java that will accept any valid program in Java and parse the Java program and say it's syntactically correct here. Now, it would be more difficult to create a Turing machine that can determine if a program can cause a runtime error. Can you write a Turing machine that can run a Java program? You should be able to do that too. But this is just, can you parse a Java program or any sort of language programs here? So, and well, it talks about the halting problem here, and we'll get to that in just a second here. So, so what is a Turing decidable language? That's different than a Turing recognizable language. So a Turing recognizable language is if it's not a language, it could loop indefinitely. A decidable language here is if W is in our language, we accept it. If W isn't in our language, then we reject it. It halts on every word. We never get an infinite loops in for Turing decidable or recursive languages here. We'll always get a yes or a no. So again, those are our two key terms, Turing recognizable or Turing decidable languages. So Turing decidable, all inputs must halt for that. So here's our language. I'm finding that this isn't putting subscripts correctly. So and let's say a simple language is a string where there's an even number of A's and B's. So every time we count the number of A's or B's or not. Another one is a language of the form of A to the N, B to the N. So we have so many A's. So we have 4 A's and we might have 4. Then we have to have 4 B's for that. So we always have the same number of A's and B's. So like samples would be just A and B, or A and B, 3 A's or 3 B's. Examples not in the language. Things like A, B. Or when we have a mixed, like we do A, B. More complex example, like the language of all prime numbers represented in binary. You can write so if you give it a number in binary, you can write a Turing machine, they can check if that number is prime or not. The primality, test is not that hard to do, and you can certainly do it in a Turing machine for any number in binary format there. And again, it's going to halt any finite size number that you put in there. It will run the test and it'll tell if that's prime or not. So. We'll get into this problem of undecidable languages and problems with halting problems. I'll just warn you that a lot of those get in these large, infinitely recursive definitions of languages. So here's an example of one of the product. So we can represent a Turing machine as a set of symbols. So we can feed definitions of Turing machines into another Turing machine there. So we can have recursively take Turing machine definitions and feed them, because it's just a collection of symbols, and feed them into a Turing machine here. So the language of all Turing machines that eventually write one on their tape when started on a blank tape there. So we don't know if that's decidable, if we can write a Turing machine that will look at every Turing machine and decide if it's going to write a one on the tape, because we can make some really complex Turing machines, feed them into this meta Turing machine and ask how it is. So so then we get into some decidable problems. Oh, I'm going to fix this format one just real quick. So the example is, can we prove that this language A to the n, B to the n is decidable for that? So for example, when n equals 0, it's just an empty string. That would be acceptable. If n equals 1, it's just A, B. If n equals 2, it's A, B, B. If n equals 3, got 3 A's and 3 B's. So we'll decide a Turing machine that will accept that. Again, I find that the chat GP, or this is like Gemini, doesn't put things, or somewhere the subscripts, the superscripts are lost often when we write these out. So how is this Turing machine going to work? First, we check for an empty string. If its input is empty, we accept there. And then we start matching A's and B's. We move the head to the leftmost A, replace that with an X, move the head to the leftmost B, replace that with a Y, and move the head back to the leftmost A and replace it with an X. And then we just repeat this stuff. So we keep switching every A that we find to an X and every B to a Y there. And if it's in the language, at some point, all the A's and B's will only have X's and Y's here. So, and again, we can write a formal definition of this machine here. So our input alphabet is A or B, but our tape alphabet is A, B, and then these X's and Y's we'll write on there. So we'll walk through some of these more formal examples later on in class on Thursday. But again, this kind of walks us through here. Here we're in state Q 0, and our tape is A, B, B, and then a space here. So we'll replace the A with an X here. So now, and then we'll move to the right for that. So we're going to replace this A with an X and move to the right here. Actually, this one shouldn't be there. Yeah, it should be that. So we're going to replace that A with an X, move to the right. And so we have A, B, B there. And we're going to keep reading until we get to the B over here. And then we're going to switch to state 2 there and change the B to a Y and move back and forth. And this is where I'm seeing AI is not the greatest at these examples, they typically will make these mistakes as they go through. At least, again, this was just not a reasoning model there. So some of the reasoning models should be better at this than this, but they'll try to do okay. So that's what we'll work with on Thursday. We'll try to work through a bunch of these examples and write these programs and try it out. So it gets us into this undecidable languages and Turing machines, some of the limits of computation. We have what is called a halting problem. One of the questions is if we're given a Turing machine and an input string, will the Turing machine halt when run on W there? And can we prove that for every Turing machine, it will halt given this input? And we run into this issue where we can't prove that every Turing machine will, well, that given a Turing machine, we can't create another Turing machine that looks at a Turing machine and an input and always tells it will halt or not there. So we can get into this idea of countability and uncountability. I don't know if you've studied infinities in math class or other places there, but the kind of the lowest level of infinity is a countable infinity, like the whole numbers or the integers are countable infinite there, but like the real numbers or the rational numbers are uncountable infinite. And so the set of all Turing machines is countable. We can list them all, but the set of all languages is uncountable there. There are more languages than Turing machines can recognize. And so when we say there's a, so there are things we can write down that aren't programs, aren't Turing machines, or that our Turing machine can't recognize for this. A lot of this works with a diagonalization argument. And I'm not going to get into explaining these arguments, but if you want to go down a fun rabbit hole, look at these. This is related to Gödel's proof that we can't, with a system of logic, we can't prove every statement with a system of logic. And again, we have the same sort of proof that Turing did with Turing machines, that there are things we cannot recognize with this sort of stuff. So again, we kind of have a hierarchy of languages. We have our deterministic finite automata here, our push-down automata, and now we're adding Turing machines and what they can do for that. And at this point, we're going to see that Turing machines are basically equivalent to modern day computers. So again, the idea is that any general purpose computer and algorithm it will be equivalent to a Turing machine and vice versa here. So I'm going to skip over some of this stuff on programming techniques because again, we'll come back to this on Thursday here. But again, some just overviews. We often will write marking symbols to the tape. We can work on shifting the tape. And again, return to the head or the far left of the tape. So again, on the far right and left of the tape are generally spaces. And so you can keep changing until you get to the far left or the far right of the tape here. So You can also, amazingly, with Turing machines, write little subroutines and stuff like that for this. So we'll look at some of these on Thursday. So again, this is just talking about how do you do modular programming, how do you do subroutines in a Turing machine, and how do you set that up here. And again, this is the example of a palindrome here, and walk through how we'd step through a palindrome there. So again, if we have these palindromes, and again, we often start with a real simple alphabet, just A's and B's here, and design a Turing machine that will accept those examples here and work on them. So again, what's the basic idea of this? So it started at state Q0, and we'll go to either QA or QB, state A or B, if we read an A or a B as the input for this. So if we're in state QA, we'll move to the right until we get to the end of the string, and then we'll replace that with A. We go to this state called Q return, where we'll return to the last state to the right, left, and replace and check if that's a B, or see if it's an A2. So basically here we'll read this A, go to this end, make sure, and we'll mark that, make sure this is an A, and we'll go back, and then we'll read this one and then this one, and then we'll be in state. If we've read an A, we'll be in state QA, and again, sometimes we just call that state 1 and state 2. That's fine. And then we have this return state. Again, we'll work through these on Thursday. We'll have you work through a number of examples. We'll do this palindrome example more on Thursday. We'll also talk about these state transition diagrams, and this is certainly a weakness of the large language models. They're trying to show these state transition diagrams. So this is state 1, state 2, state 3 here, and the accept state. This is kind of what our inputs are and what our outputs are, I think. Again, it's just not done very well with text. So we'll have you draw these out like this here. And we'll look at some syntax for these. So where if you're reading either a 0 or a 1, there you will move to the left. If you're reading a 0, 1, you'll move to the right here. If you're reading if you're reading a 0 and you'll change it to a 1, and then you move to the left here. And here, if you're reading a 1, you'll change it to a 1 and move to the right for this. So again, we'll look at these sorts of state transition diagrams for these different values. There's also some nice, I won't bring them, but they're nice online simulators for Turing machines. So we'll look at those on Thursday also. I think those are kind of helpful for this. Now, besides these diagrams, sometimes we write it out as a state transition table. So here's our different states. Here's our inputs. And here's what our next state is. Here's what we're writing, and here's what we're moving. I really like state transition tables like this. Again, we can write out the rules, but I love any Turing machine with a set of rules you can write as a set of states like this. And I really like it this way. I think it's very clear. So if you're in state 1 and you see a 0 on the input, then you stay in state 1, you're going to write a 0 and you're going to move to the right. And if you're in state 1 and you see a 1, now you're going to switch to state 2, you're going to write a Y and move to the left, sort of idea. I really like these sorts of state transition tables to make it clear what's going to happen. we need to talk a little bit about theory here and some of the philosophical implications of this stuff. So first we need to talk about what problem reduction is. We're going to see this a lot when we get to complexity and like, can we do this in a polynomial amount of time? There are what we call P and NP non-polynomial time and polynomial time problems here in complexity theory. And one of the things we'll do is we'll work on reducing lots of problems to other problems and saying, well, if we could do this in polynomial time, we can do this in polynomial time there. And so we see the same thing with Turing machines and undecidability, is that with problem reduction. Can we reduce one problem to another? So if we could solve one problem, it shows we can solve another problem here. So problem reduction is a technique we'll use to show that one problem at least as hard as another problem. So if we could solve problem A, we could solve problem B here. So if you can create a Turing machine that can map one problem into another problem, and you can solve that second problem with the Turing machine, then you could solve the first problem with a Turing machine. So for example, we just talked about a Turing machine that can determine if a binary number is prime there. That's decidable. We know that. We can write a machine plan. But what if it's in decimal format? Well, you can create a Turing machine that'll take any decimal number and rewrite it as binary. So there's a Turing machine that'll convert every decimal number into binary, and there's another Turing machine that'll check if any binary number is prime. So obviously there's a Turing machine that can combine those two Turing machines and check if any decimal number is prime there. So again, that's kind of how we can look at transforming a problem. So if we have an instance of problem A, we transform it to an instance of problem B. So if we have a decimal number, we know how to create a Turing machine to transform that into a binary number. And once we add it in binary form, we can solve the problem B. We know a solution. We have an algorithm for a Turing machine that solves that problem B for that. So we can look at all sorts of problems and know which ones we can solve. And again, if we get a new problem, if we can just map it onto a solved problem, then, if we can have a Turing machine that kind of converts it into something we know how to solve, then we're good there. The problem is that if there are problems that aren't decidable there, what does that mean? So, So again, this halting problem is given a Turing machine M and an input string W, will M eventually halt or stop when run on W? Can we create a Turing machine or any algorithm that can analyze another Turing machine and its input and determine whether or not it'll eventually halt or run forever? So this is the idea of this halting problem, and we're going to create this kind of solution. To tell you the truth, I've never liked these infinite diagonal kind of cases. I don't like Gödel's theorem of undecidability, and I don't really like this Turing stuff. From a philosophical point, it kind of makes sense, but maybe I'm not philosophical enough to see this stuff. But all of these rely on this kind of self-contradiction sort of stuff. So in order to do this, we say, let's assume for the sake of contradiction, there exists a Turing machine H that can solve the Turing problem. So let's say we have a Turing machine that can take any input, take any machine and any input and solve that problem. So we have what we're going to assume for the sake of contradiction that that is true, and then we're going to prove that it can't be true there for contradiction. So H takes input of a Turing machine M and an input string W, and it outputs halts or loops here. Now we're going to construct a new Turing machine D that uses H as a subroutine here. So we're going to make a new Turing machine that uses this machine that we assume exists here. And so now D takes input of a Turing machine, and we're going to see if we run the Turing machine M, and its input will also be M for this, and it will halt or not here. And then we can get into this contradiction. Again, it gets confusing because remember, we've got a Turing machine, which we can specify as a sequence of letters, and we have inputs. And so we can use a Turing machine as input into another Turing machine here. That's why we have our Turing machine where we're giving it some machine and we're feeding that same machine as input into it here. And then we can create our contradiction based on that. And again, almost all these logical proofs require this sort of recursive definition, assuming something's true and then using that, feeding that in on itself there. So they try to explain this in English. Think of, creating a program that can analyze any other program to tell you whether or not it will ever get stuck. Turing proof that says, or an infinite loop, and Turing proof shows that's not possible because we can feed if we had a program that could do that, we could kind of feed it into itself and trick it, or not trick it, but set up an instance where it's never going to happen. So from a philosophical point, why is this important? It just means that there are some limits to computation. There are some things where we cannot, there are some problems that we're not going to be able to solve with Turing machines. Some things are not computable, basically. And some people really take that and go from that on here. So again, this raises questions about the nature of computation, human knowledge here. Challenge this idea that everything is mathematical for this stuff. What this, and I'm trying to remember where this is, what this sometimes is used is to talk about artificial intelligence and the limits of computational intelligence, and say that, the question, a lot of people say, argue that the mind can be equivalent to a Turing machine, and that everything is very predictable. Here, let me jump down. I think this is, oops. I'm going to jump down here and we get to this Church-Turing thesis and explain what that is. The idea is that every effectively computable function is computed can be computed by a Turing machine. And then we can say anything that's effectively computable, so anything that can run on a mechanical process and an algorithm, can be shown to be equivalent to a Turing machine. So this is just a thesis, but the idea is that a lot of people agree with this, is that Turing machines kind of define everything that's computable for that. So anything that has, and so what is a reasonable model? Anything that can be broken up into discrete steps, have finite instructions, finite memory, and potential unbound memory here. So things like lambda calculuses, recursive functions, post machines, just modern programming languages, all that are equivalent to each other in some ways, and equivalent to a Turing machine for this. Again, this is a thesis, not a theorem. It's a belief supported by external evidence. It can't be formally proved here, but a lot of people feel this way, and it impacts them. So, so here's an example of some of the implications, the computational theory of the mind. So the brain is a physical system, and physical systems can be simulated computationally there. And so the brain processes might be simulated by a Turing machine. So the question is, do you feel that that is true? Do you think that the brains and your thinking can be simulated by a Turing machine? And what does that mean for that? So, and people will argue back and forth on that. Like a couple arguments you can make is that there are specific requirements of this. So one of them is discrete steps, that our algorithm works in discrete steps. And you could argue, well, the brain doesn't have a clock. It's not working in discrete steps there. It's a continuous analog version of this. And so it doesn't necessarily fit a Turing machine. And so the brain is beyond what can be done with the Turing machine there. Other people argue, well, any sort of system with analog system, we can simply time slice, we can simulate it with slices of time. And if we set the time slices small enough, we can emulate and predict the output of any physical system so that you can make it equivalent to a Turing machine. So again, this has implications that we might say it, AI should be able to simulate anything the brain can do there. But again, people will talk about things like consciousness and creativity being something that doesn't, arises more spontaneously or is beyond just the brain there. And we talk about this mind-brain difference there. And so people will say that, that in human intelligence is not the same, that there's more to being human than a Turing machine, I guess, for this stuff. What is your thoughts on that? Do you think at some point, do you think that we can, that there's not really any fundamental or theoretical difference between what a computer does and what the human brain does? Or is there something different there? Yeah, it kind of gets to some of your feelings on what you think it is to be human there. Is there stuff to being human that's beyond just the physical realm of things or not? And kind of, within science there, if we're just looking at the physical world, then you can have a pretty their argument, or people make the argument that the brain is the physical system. We can model that, but people will argue that that's different. It's interesting. A lot of people used to bring up creativity in this and saying that human creativity is different than this, and that you can't simulate, you can't, a Turing machine can't be creative. But nowadays we have these AI systems that seem to be very creative and very, generating images, writing poems, writing songs, almost any sort of creative endeavor. We now have AI systems that can simulate that. And so is there any difference between being creative and simulating creativity in those models for this? One thing to be aware of is that the Turing machine is very deterministic here. And so we can get into this idea of determinism versus free will. And so a Turing machine is very deterministic. You can always predict its behavior. So then the question is, if the brain is like a Turing machine, is the brain just very deterministic, and is there free will, or are we just reacting to stimulus with a predictable pattern for that? One thing I often think those sorts of questions skip is that although Turing machines and all computers are deterministic, we can generate random numbers, and we can do what we have what are called stochastic or random processes there. Now, true, we can't generate true randomness, but we can do pseudo-random numbers, and we can get really good pseudo-random numbers that are basically, for all practical purposes, indistinguishable from random numbers there. And so if we can generate randomness in a deterministic system, then what does that imply for this? So I never quite got the philosophical, I don't know if I'm deep enough, question of, does that mean that free will is an illusion there? I guess maybe I never thought I had free will. Maybe that's my problem, is that I think I just react to stimulus there, and I don't know where free will comes into that, but so, okay. Let's wrap this up. So again, that's kind of jumps into our theory stuff. Thursday, we'll get much more into practical programming of Turing machines there. I haven't done the learning exercise or the assignment yet. I'll have those done by tomorrow. But again, we'll be programming them. We'll be writing state transition diagrams for these, and we'll be simulating them on a computer. We can simulate a Turing machine. They're nice simulations online, so we'll be doing that. So we'll be programming Turing machines on Thursday. Sound good? Okay. Imitation Game. Yeah, that's the movie that everyone should watch. If you haven't seen the Imitation Game, you should watch that. So, okay.